Alright, Chapter 3, Module 5, Neets, Navy Electronics Training Series. Chapter 3, Alternating Current Generators. Learning Objectives. Upon completion of this chapter, you will be able to describe the principal magnetic induction that apply the AC generators, describe the difference between the two basic types of AC generators, list the advantages and disadvantages of the two types of AC generators, describe exciter generated with the alternators, discuss the construction and purpose, compare the two rotors used in generators, the application of each of the type of the different primary movers, explain the factors determine the maximum power out of an AC generator, the effect of these factors rating generators, explain the operation of multiple-phase AC generator, compare the single-phase, describe the relations between the individual output result and victorial sum voltage in the multiple-phase generators. Explain the use diagram of the different methods of connecting three-phase alternators and transformers. Lift the factor to determine the frequency voltage alternator output. Explain the term voltage control voltage regulation as an AC generator. List the factors each of the effect quantity. Describe the purpose of procedural parallel generator operation. Introduction. Move with electrical power used by the board of Navy ship the aircraft will be civilian applications of AC. As a result of the AC generator's most important means of the producing electrical power, AC generators are generally called alternators. Vary greatly in size depending upon the load which they apply the power for. Example, the alternators are used in hydroelectric plants such as Hoover Dam and tremendously in size grid generating thousands of kilowatts at a very high voltage level than any other example of the alternator in which the type of the automobile, which is very small comparison. It weighs only a few pounds, produced between 100 and 200 watts of power, usually a potential of 12 volts. Many of the term principles covered by this chapter will be familiar to me. The same as those covered in the chapter of the DC generators. You encourage to refer back as you need to refer to any other source that will help you to master the subject of the subject of this chapter. No one source meets the complete needs of everyone. Our basic AC generators, regardless of the size of all electrical generators, whether AC or DC, depend upon the principal magnetic induction EMF inducing the coil as a result. 1. Coil cutting through the magnetic field. 2. Magnetic field cutting through a coil. As long as there is relative motion between the conductor and a magnetic field, the voltage will be induced. The conductor, the part of the generator produced the magnetic field, is called the field. This part of the voltage induced is called the armature. For the relative motion to take place between the conductor and magnetic field, all generators must have two mechanical parts, a rotor and a stator. The rotor is the part that rotates, the stator is the part that remains stationary. In DC generator, the armature always rotates. The armature is always the rotor. In alternators, the armature may be either rotor or stator. Rotating armature or alternators. Rotating armature or alternators, some similar construction for the DC generator is in the armature of the rotating station magnetic field is shown in Figure 3.1 View A. But the DC generator is the EMF generated by the armature windings covered from AC to DC by means of the commutator. If the alternator is generated with the AC brought with the load unchanged by the means of the slip rings, the rotation armature is found only in the armature with low power rating. Generally is not used to supply electrical power in large quantities. Alright, A shows the rotating armature alternator field, the field excitation armature AC output, rotating the AC output field, field excitation, rotating field alternator. Rotating field alternators. A rotating field alternator stationary armature winding of the rotating field with the which winding shown in Figure 3.1 View B. The advantage of having the stationary armature winding is that the generated generated voltage can be connected directly to the load. A rotating armature requires slip rings brushes to conduct the current from the armature to the load of the armature brush. With the slip ring, the difficulty to insulate with the arc cover, the short circuit can be reduced on the high voltage. For the reason high voltage alternators are usually rotating field type, since the voltage applied with the rotating field is lower than low voltage DC. The problem high voltage arc over slip rings does not exist. The stationary armature or stator of the type of the alternator hold the winding that are cut by the rotating magnetic field. The voltage generated by the armature result with a cutting action in the AC power will be applied to the load. The stator of the all rotating field alternators are the same, or about the same. The stator consists of the laminated iron core with the armature windings embedded in this core, shown together E2 with the core is secured with the stator frame. Stationary armature winding slots, and stator assembly laminated core. Alright, practical alternator. Alternators described so far in this chapter are elementary in nature. The seldom used examples and understand the practical alternators. Remember, the chapter will be presentable with the alternator, elementary alternators actually with the civilian community as well as the Navy, ship, and the aircraft. The following paragraphs in the chapter will introduce the such concept of the primary move of the field fixation, armature characters, limitation, single phase, polyphase, alternators, control, regulation, and parallel operation. Function of the alternator components. Type of the rotating field of the AC generator consists of the alternator smaller DC generator built into the single unit, the output of the alternator section, and supply of the alternating voltage of the load. The only purpose of the DC exciter generator is to supply the direct current required to maintain the alternator field. This DC generator is referred to as the exciter. The type of the alternator is shown in Figure 3 view A. Figure 3 view B is simplified schematic of the generator. Alright, so you have your AC field input, slip ring, exciter output, and exciter generator armature, AC field windings, rotor drive shaft, and then you have the exciter DC generator section, commutator, slip rigging, section, exciter control terminals, AC power output terminals, AC generator section, drive shaft, the exciter control terminals, exciter generator, exciter armature, exciter field windings, AC generator rotating field windings, alternator field armature winding, three-phase AC output terminals. Alright, the exciter of the DC shunt wound self-excited generator. This exciter shunt field creates an area with the intense magnetic flux between the pole of the exciter armature is rotated with the exciter field flux. Voltage induced the exciter armature winding. The output with the exciter communicator 4 is connected through the brushes and slip rings to the alternator field 6. Since the direct current is already converted by the exciter communicator, the current always allows the flow in one direction through the alternator field. 6. The fixed polarity of the magnet field maintained at all times of the alternator field windings. When the alternator field is rotated, the magnetic flux is passed through and crosses the alternator armature windings. The armature is wound in for a three-phase output, which will be covered later in this chapter. Remember, a voltage is induced in a conductor if the stationary magnetic field is passed across the conductor. Same field the stationary conductor is moved. The alternator voltage in the generator armature winding is connected through the fixed terminal to the AC load. Primary movers. Prime movers. All generated large-scale AC/DC require a source of mechanical power to turn the rotors. The source of the mechanical energy is called the prime mover. Prime mover is divided into two class generators: high-speed, low-speed, steam, gas, turbines, high-speed power movers, internal combustion engines, water, electrical motors, and considered low-speed prime movers. Type of the prime mover plays an important part of the design of the alternators, since the speed at which the rotor is turned determines the characteristic of the alternator construction and operation. Alternator or rotator. The two types of the rotators used in the rotating field alternators are called turbine-driven or salient pole radiators. As you may have guessed, the turbine-driven rotor shown in Figure 3 view A is used when the prime mover is a high-speed turbine winding with the turbo-driven rotor arranged for form 2 to 4 distinct poles. The windings are firmly embedded with the slots to withstand the tremendous central vigor forces encountered with the high speed. So you have your turbine-driven high speed of 1200 RPM, salient pole rotor 1200 RPMs or less, slip rings, cross-section of the line of magnetic force. Salient pole rotors shown in Figure 3 is used with the low-speed alternator. Salient pole rotors often consist of separately wound pole pieces at the bottom of the frame of the rotor. If you can compare the physical size of the two types of the rotors while the same electrical characteristics, you would see that the salient pole rotor would have the greater diameter, as the same number of revolutions per minute, has a greater central vigor force than does the turbine-driven rotor. To reduce the force to a safe level so that the windings will not be thrown out of the machine, the salient pole is used in low-speed design. Alternator characteristics and limitations. Alternators are rated according to the voltage they design to produce the maximum current that they are capable of providing. The maximum current can be supplied with the alternator dependent upon the maximum heating loss that can be sustained with the armature. The heating loss which is the amperage squared over the resistance, or ohms loss at the x to the heat of the conductor successfully destroy the insulation. The alternators are rated in terms of current. In terms of voltage output, alternator rating is small unit in the volt amperes, the large unit with the kilovolt amperes. When alternator leaves the factory, it's already destined to do a very specific job. The speed at which it is designated to rotate the voltage will produce the current limits. The other operating characteristics are built. The information usually stamped on the nameplate. On the case of the users will know the limitations. Alright, your single-phase alternators generally produce a single continuous alternating voltage known as a single-phase alternator. All alternators have been discussed so far fit in this definition. The stator armature windings are connected in a series of individual voltages, therefore are added to produce a single-phase AC voltage. The Figure 3.5 shows the basic alternator single-phase output voltage. So you have a single-phase positive negative. You feel like if this was a transformer, but it's not, so it's a rotor, so there you go. The definition phase you learn in studying AC circuits may not be helpful to you right here. The out of phase means out of time. No, it may be easier to think of the word phase meaning the voltage in a single phase. This is the need for the modified definition phase. The usage will be easier as we go along. Single-phase alternators are found in many applications. They are most often used when loads are being driven relatively light. Reasons for this are more apparent when we get the multiple-phase alternators called the polyphase power. They're used in these homes, shops, ships, and operatable, portable, small appliances. Single-phase power. The single-phase power alternators always generate single-phase power. However, the single-phase power does not come on from single-phase alternators. This will sound responsible. This sounds more responsible to you as we get the next jobs. Alright, your two-phase alternator. Two-phase input. Two-phase implies two voltages. We'll apply the new definition phase. That is the simple but the two-phase alternator designed to produce two complete separate voltages. Each voltage by itself must be considered a single-phase voltage. Each generated completely independent of the other. The certain advantages are gained. These mechanics are generated will covered by the following paragraphs. Alright, generation of two-phase. The show of the simple two-phase alternator. Note the windings of the two-phase physical places are read at 90-degree angles. To each other, which accept the outputs of each phase 90 parts or 90 degrees apart. The graph shows the two phase 90 apart with A leading to B. Note that they are using the original definition from the previous modules. We see that A and B are 90 degrees out of phase. They will always be 90 degrees between the phase of the two-phase alternator. This is by design. So here is a two-phase alternator. Shows the 90 degrees different. Out of phase, your wire schematic, A, B, A. Now let's go back and see the similarity difference between the original single phase alternators and the new one two phase. Note the principle will apply with the not new. The alternator works the same as the others we discussed. Stator finding figure 360 with the two single phase windings completely separated from each other. Each winding is made of the two windings that are connected in series so that their voltage is added. The rotor is indicated that you have the single-phase alternator left-hand schematic. The rotor poles opposite of the winding phase A. Therefore, the voltage induced in phase A minimum. Voltage induced in phase B is 0. The rotor continues to rotate counterclockwise. It moves always with the A windings approaching the B windings. As a result, the voltage induced in the phase A decreases the maximum value of the voltage. Increases therefore the voltage induced in phase A minimum and the voltage induced in phase B is 0. The rotor continues rotating counterclockwise. It moves always from the A windings approaching the B windings. As a result, voltage induced in phase A decreases the maximum value of the voltage induced in phase B increases 0. The right-hand schematic of the rotor poles are the opposite of the winding of the phase B, but the voltage induced in the phase B is maximum, where the voltage induced in the phase in a phase, the drop of 0 to the 90-degree rotation of the rotor corresponds to 1/4 circle to 90 degrees electrical degrees. The waveform pictures show that the voltage induced in phase A and phase B of that one cycle. The two voltages 90 out of phase. Note the two outputs, the A and B, independent of each other. Each output with a single-phase voltage, just as if the other did not exist. The obvious advantages so far that it will have two separate output voltage, the same as having one set of bearings, one rotor, one housing, so that you can do the work with two. These disadvantages have twice as many stator coils that requires larger and more complex stators. The larger schematic figure 3.7 shows the four separate wires brought out from A and B stator windings. The same is known in the figure 3.6. Notice, however, the dotted wire now connects to one end of the B1 and one end of the A2. The effect making the concentration to provide a new output voltage. The sin wave voltage C with the picture is larger than either A or B. The resulting adding of the instantaneous value of this phase A and phase B. For this reason, appears exactly halfway between A and B. Therefore, C must lag at least by 45 degrees and lead by 45 degrees. Also shown in special vectorgram. So you have a two-phase three-way alternator winding, A1, A2, B1, B2, 90 degrees in volt. Alright, now look at the smaller schematic diagram in figure 3.7. Only three connections have been brought out of the stator electrically. The same large diagram above than 7 that was being connected to the output terminals B1 and A2 connection was made internally with the stator as was wired. Two-phase alternator connected to the mainer and called the two-phase three-wire alternator. The three-wire connection must make possible three different load connections, A and B across the phase and C across both phases. Output at C always is 1.414 times the voltage either phase. Multiply outputs. Additional advantages. Two-phase alternators over the single-phase type. Note that you can understand the single-phase cover power does not apply with only come from single-phase alternators. It can be generated with a two-phase alternator as well as a multi-phase polyphase alternators, as you will see soon. Two-phase alternators discussed for the preceding paragraph seldom seen in actual use. However, the operation of polyphase alternators is more easily explained in the two-phase than three-phase. The three-phase alternator, which will be covered next, is far most common of all alternators used today, both military and civilian applications. Alright, your three-phase alternator. Three-phase alternators names imply by the three-phase windings with space in it so that the voltage induces any one of the phase discussed at 120 degrees over the two. Schematic diagram of the three-phase data shows that all the coils becomes complex. It's difficult to see what the actual happening. This specified schematic figure 3.8 view A shows all the winding each phase lumped together as one winding, and the rotor is omitted. The simplicity of the voltage waveforms generated across each phase drawn on the graph. Placed at 120 degrees from each other. The three-phase alternator is shown in the schematic made up of three-phase, single-phase alternator generated voltages are out at phase at 120 degrees. The three phases are independent of each other. Show the three-phase alternator. Three-phase Y connection and three-phase delta connection. Rather than 6 leads coming out of the three-phase alternator, the same leads each of the phase connected to form a Y connection, is shown figure 3.8 view B. It is also called the Y connection because the neutral windings appear in letter Y. In this case, sideways, ups and down. Neutral connection brought on the terminal with a single-phase load must be supplied by the single phase as well, with available the neutral A, neutral B, and neutral C. In three-phase Y connection or alternator, the two voltages line voltages across the two or three lines lead with the vector spectrum. Vector sum of the individual phase. Each line with the voltage 1.73 times 1 over the phase volts. They cover the windings from ORM. Only one half of the current flow from between these lines. The line and phase currents are same equal. A three-phase stator can always be connected so the phase and connected to the end-to-end is now delta connected to the figure. View 3.8 delta because it looks like a Greek letter delta. In delta connection, the line voltage equal to phase voltage, and each line current is 1.73 times the phase current. Both Y and delta connections are used in alternators. Majority of all alternators in the Navy today are three-phase machines. They are much more efficient than either two-phase or single-phase alternators. Three-phase connections. Stator coils with three-phase and alternators may be joined together in either a Y or delta connection, shown in figure 3.9. While the Y connections on the only three wires come out of the alternator, this allows the convenient connection of the three-phase motor power distribution transformer is necessary to use the three-phase transformer of electrical equivalently to this type of system. Show the delta connected, Y connected. Figure 3 show the three-phase alternator transformer connections. A three-phase transformer made up of three single-phase transformers connected to the delta-Y combination, both the primary and secondary connected in a Y transformer, and they'll call it the Y. If both windings are connected to delta, the transformer is called the delta-delta. Shows a single-phase single transformer to delta operation three-phase system. Will note the transformer windings are not angled and illustrate. Typical delta has the done with the alternating windings. Physically, each of the transformer diagram stands alone. There is no angular relationship between the windings and the individual transformer. However, the following the connection, we'll see that the electric delta primary windings, for example, come connected to each of the other closed loops. Each of the junction is fed with the phase voltage for a three-phase alternator. Alternator may be connected to either delta or Y, depending on the load or voltage requirements designed in the system. Alright, this shows the three single-phase transformer connected delta to delta. You have a three-phase input primary, three-phase single output secondary. That's your transformer. Notice the iron core. Three-phase 1, 2, 3, just like a Figure 311 shows three single-phase transformers in a Y. Again, note that the transformer winding is not angled. The electrical Y is formed with a connection. The lower connections of each winding is shorted together. These form a common point of the Y. The opposite end of the Y is isolated. The ends of the arms are arms of the Y. Shows your three-phase input primary phase for a Y connection. Notice the transformer, 3-foot Ys. The AC power on most ships is distributed in three-phase, three-wire, 400-volt system. The single-phase transformer step-down voltage of 117 volt. The transformer connected delta to delta in Figure 310. With the delta-delta configuration, load may be three-phase device connected to all the phases, and then may be a single-phase device connected only to one phase. At this point, it is important to remember that such a distribution system includes everything between the alternator and load, because of any of the many choices of the three-phase system provided, care must be taken to ensure that any change of connections does not provide the load with the wrong voltage or wrong phase. Your frequency. Output frequency of an alternator voltage depends on the speed of the rotation of the rotor, the number of the poles. The faster speed, the higher the frequency. The lower the speed, the lower the frequency. The more poles that are rotors, there on the rotor, the higher frequency of the given speed. When a rotor has been rotated through an angle such that the two adjacent rotor poles, north and south, have phased past one winding of the voltage inducing the winding that will have varied through one complete cycle, having given the frequency more poles, there are lower speed rotation. The principle illustrated in Figure 312. The whole pole generator most rotate 4 times speed with the 8-pole generator to produce single frequency generated voltage. The frequency of an AC generator is in hertz when the number of cycles per second is related to the number of the poles and speeds of the rotation accepted and expressed in this connotation. Frequency of the number of the poles over 120 cycles. Where two poles and the speed of the rotation revolutions per minute. 120 is the concept of the conversion of minutes into seconds. From pole to the pair of poles, for the example, 2 poles, 360 RPMs at the frequency of 60 hertz is determined by 2 poles times 360 RPMs over 120 seconds is 60 hertz. A 4-pole 1800 RPM has a frequency of 60 hertz. A 6-pole 500 RPM generator has a frequency of 6 times 500 RPMs over 120 seconds is 25 hertz. 12-pole 4000 RPM generator 12 times 400 over 120 is 400 hertz. Both alternators rotating at 1200 RPMs. Note that the number of poles frequency is equal to the number of the poles over 120. The 8-pole low speed 180, 360. 2-pole low speed. Voltage regulation. We see that this is seen before. The load of the generator's chamber, the terminal voltage varies. The amount of the vary depends on the design. Generator voltage regulation over the alternator's chamber, the voltage full load, no load, expresses the percentage full load volt. When speed of the DC field current are in constant, the voltage of the number of conductors and the number percentage of regulation. Assume that volts no load, volts frequency load over volts frequency load times 100. A percent of volts no load voltage number of frequency voltage no load voltage minus number full load voltage over divided by voltage full load or by times 100 percentage regulation. Assume that no load voltage alternators at 250, full load voltage at 250, 220. The percent of the regulation would be 250 minus 220 over 220 times 100 at 13.6. Remember, the lowest percent regulation, the better is most of the applications. Principle of AC voltage control. The alternating voltage produced for the armature winding of the magnetic field for the alternator pole is passed across the windings. The amount of the voltage induced in the windings depends mainly on 3 things: the number of the conductor in series per winding, the speed of the alternator, RPM, the static and the magnetic field of the cutting of the winding, the strength of the magnetic field. Any of these 3 factors can be used to control the amount of voltage induced in the alternator. The number of the windings, of course, is fixed when the alternator is manufactured, although also that the output of the frequency required the constant value of the speed of the rotating field must hold the concept of prevent the use of alternating RPMs move the control of voltage output. Thus, the only practical method of obtaining voltage control is to control strength of the rotating magnetic field. The strength of the electromagnetic field may be varied, changing the amount of current through the flow through the field coil to accomplish varying amount of the voltage applied with the field coil. Parallel operations. Alternators connected in the parallel increase the output capacity system beyond a single unit to serve the additional reserve power for the accepted demands. 3 permit shutdown of one of the machine, cutting down the stand by the machine without interrupting the power distribution when the alternators are sufficient size that are operating a different frequency of the terminal voltages. Severe damage may be the result of the suddenly connected to each other through the common bus. To avoid this, machine must be synchronized as closely as possible before connecting them together. They may be accomplished by connecting one generator to the bus referred to as the bus generator, then synchronizing the other with the incoming generator before the closing incoming generator main power contact. The generators are synchronized if the following conditions are set. Equal terminal voltage is obtained with adjusting the incoming generator field strength. Equal frequency obtained with adjustment with the incoming generator's prime and remove their speed. And phasing voltage for the proper phase relation of the produced. The synchronizing generator is not discussed in the chapter. At this point, it is enough to know that the above must be accomplished to prevent damage of the machines. Alright, Chapter 3, Summary.